Okay, welcome to the second class. So first I want to make a point on the relation between thermodynamics and kinetics. So you know this course will be mostly on kinetics, but it's interesting to just consider to what an extent a reaction can proceed, right? So that we get from thermodynamics. Dynamics. Okay, so let's consider a reaction. This one. And we know that the standard Gibbs energy change, so delta G, of this reaction at 600 degrees Kelvin is 23.17 kilojoule per mole. Okay, so the equilibrium constant Kp can be expressed in terms of the degree of advancement of the reaction. So that means if this is 0, that means no reaction. And if it is 1, it's 100% reacted. Okay, so let's look at the expression. So we have delta G naught minus R times T times ln that squared 1 minus. Okay, and that leads to, we take that out, right? Exponent minus delta G naught over 2RT equals 0.0981, and from that we can calculate the degree of advancement, 0.16. So that means only 16.4% of the reaction will proceed at 600 degrees. So that means that the equilibrium is mostly on one side, right? So that's important to remember. So when you have an equilibrium, it will not go all the way. So for example, in the little quiz question I asked in the previous class, when you go from, if you have two molecules of A, one molecule of A, one molecule of B that are in equilibrium with C and D, you, in that case, it was kind of a trick question, not really, but you will have, for example, A and B converting to C and D, and then C and D converting back to A and B. So you have a kind of flip-flopping of the reaction all the time at equilibrium. So that's important to remember, that at equilibrium you have a forward rate, you have a backward rate, and they are the rates of these reactions are at the same. So overall nothing changes, but still molecules are being changed. So that's thermodynamics, right? We know the degree of advancement of a reaction, but we have no idea, how does this degree of advancement go versus time? Does it go linear? Does it go like this? We have no idea. So that's where kinetics comes in. Okay, so let's start with a very simple case. Simple case. Okay, let's say we have A, compound A, that is transformed to B. So what's the rate of the reaction? So this is reaction, right? Rxn. So in a lot of books that's called V, and that will be dt. So that means the concentration of B. So these brackets, the square brackets, means concentration, right? And so the change of concentration versus time will be opposite for A. So A is disappearing. So we'll have minus A dt. Okay. So what if you have multiple reagents? Let's say you have A plus 3B goes to C plus 2D. Okay, so there's only one reaction rate, right? But you have different stoichiometries for the reaction. So we have, let's say, N A times A, you have NB times B, NC times C, and ND times D. Right, so if we look at the velocity or the rate, V, it will be minus dA dt. It will be minus 1/3 dB dt. C is just 1, right? So it will be dC dt and half dD dt. Right? So we can see that there are different ratios depending on the stoichiometry, but there's only one reaction rate in the whole system. Okay. So let's say we have reaction A plus B goes to C plus D. Right? We have the rate is K times concentration A times concentration B. Right? So this K is the reaction rate constant. That is independent of concentration. But as we've seen in the previous class, dependent on temperature, for example, but also on pressure, ionic strength, the solvent, right? So if you look at the the dielectric constant of the solvent, that can really affect your reaction. So now comes a very important point, right? In general, the reaction rate or the order of the reaction has to be determined experimentally. So you will see later on, we will do many times this approximation, but in a most general way, you have to determine these coefficients, right? And that's the order of the reaction. That's the order of the reaction in A, the order of the reaction in B, in C. And this is not always just a simple function. No, it's not a priori. When I show you a reaction, you cannot always write down the correct rate equation with the right order. So, for example, if we take hydrogen gas plus bromine gas, right? We get HBr, two of them, gas. So you would, very simply say, okay, we have a certain rate constant K, we have V equals K times H2 times Br2, and we're done because, here's a 1 and here's another 1. So this must be 1 and 1, right? So no, actually it's not. This is wrong. Actually what it is, it's this, K times H2 times Br2 to the 3/2 divided by Br2 plus K dash HBr. And now you're like, how am I supposed to know that that's true? Right? And it's because many times when you look at the reaction, this is not an elementary reaction. It's actually, there's a much more complicated mechanism behind it that you don't know when you're simply doing the reaction. So very briefly, just as a side note, you actually first have an equilibrium where you have a forward rate K1 and a backward rate K minus 1. And then after this equilibrium, you have the first reaction that goes like that, and that's followed by this reaction plus Br, right? And that's much more difficult and complicated than what we thought initially, maybe. So that's why reaction order should not be confused with stoichiometry, but has to be experimentally determined. Then there are, you will see later, there are conditions where, in solution at dilute concentrations, these, let's say the stoichiometries and the orders can often be the same, but it's not a general situation. So you have to be a bit careful with that. And if you look at the field of catalysis, if you look at gas phase reactions, it's very commonplace to experimentally determine the order in each of the reactants, and that also tells you something about the mechanism of these reactions. Okay, so reaction order, to emphasize it again, reaction order is not to be confused with the stoichiometry. So let's go again to the simple case. A plus A gives B, right? So V rate will be K times A is K times A squared, right? So what you would say is the reaction has order 2 in A. If we take 2A plus B gives C, then we have a rate K times A squared times B. So you say the reaction has, you can say, partial order in A and 1 in B, and the total reaction order is 3. Right? So in general, you have rate is concentration A to the power A, B to the power B, C to the power C, etc. And the total order N will be A plus B plus C plus whatever. Okay. Let's go start very simple. So we start with 0th order. A 0th order reaction, the rate equation is very simple. It's just equal to the rate constant. So if you are measuring some concentration, it will be just K times T, right? It will be linear, right? So if we measure, some concentration versus time, we'll just get a straight line that does not depend on any concentration in your species, of any of your species. Okay, that's simple. First order. Okay, we go back to our simple example. A goes to B with a certain rate constant K. So I can write dA dt, right? So it's my differential equation minus K times A. Okay, so let's first look at the analytical approach to solve this, right? How do I do that? So I integrate from A0, that's my concentration of A at time 0, up to my certain concentration A at a certain time. dA d over A, right? I'm splitting just as normal integration. I'm splitting the variables to the two sides. So I bring A to the left and I have minus K dt on the right, which I integrate from time 0 to time t, right? And then you all know that this is ln A over A0 minus K times T. Okay, so if we write that out, we have concentration of A will be concentration A0, right? So you will see that over time we will start leaving these brackets out just to save some space, right? So in here, K has units seconds minus 1. It's like a frequency, like 1 over second. So now we're going to let's say if we plot that versus time. Oops, try to do that better. Right, if we try to plot that over time, we'd have something like this, right? So if we have concentration A versus time, we would get this kind of plot. If we would plot, of course, ln of A versus time. What will we get? We will get a straight line where the slope is minus k. Okay, so you'll see that especially in the beginning of the field of kinetics, people were many times plotting their concentrations on logarithmic paper and then using a ruler to actually fit the slope of this reaction. Okay, so there are two important ways of quantifying in different ways your reaction. So we have, of course, the reaction rate constant, we have initial concentrations, but there are two important concepts. Okay, one is called half-life. Okay, half-life, what does that mean? It means the time needed to get to half the initial concentration. So let's say if we start here at concentration A0, then I'll read off that value. I call it, let's say for simplicity, 100%. Now I look here, when do I reach 50%? Tuck, 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 tuck. I go here, I have this time. This time I call the half-life, right? Half-life of the reaction. And that I call T half. So how do we know what that is? We just have to plug it basically into this equation, right? So let's bring that here. So if we say that minus K times T half is equal to ln of half the original concentration divided by A0. So A0 cancels out. We're left with ln half, which is that. We multiply everything by -1, so we get plus kt minus this, minus ln of a half is ln 2. Right? Because ln 1 is 0. And then we get T half is ln 2 over K. Right? So that's pretty nice. So if you have a first order reaction, you simply have to look in your experimental trace. Okay, when do I reach 50% concentration? That's my T half. ln 2 over K is T half. Well, you have found your K value already. You'll see that in practice, of course, we'll do more like nonlinear regression to get accurate values of K, but it gives a first indication. And second concept is the lifetime. And that is tau. And for first order, that's simply 1 over K. Okay. Let's move to second order reaction. Okay, so let's say we have A plus A gives a product P with rate K. So we have half dA dt is minus K times A square, right? So that's important to keep in mind that we have this factor half here because we have 1A here, 1A here, we have 2 A's. So because of stoichiometry reasons, we have to put half in front of the overall rate. Okay. Other simple example. A plus B give P, dA dt in this case would be minus k times A times B. Okay, so one way of solving this second order reaction is considering the concentrations of A and B at a certain time. So let's say at t equals 0, the concentration of A and the concentration B, I call it small a and small b. Then when you're at a time equals t, which can be any random time, you have the original amount of A, which is small a, minus x. That is what has been consumed already, right? And for B, we have the same as well. So those are the concentrations at time t. So if we write now the reaction rate in this form, we get dx dt is, so we'll call this K2 for second order, A minus x, B minus x. So I didn't really do anything, I just put A minus x for concentration of A at time t, and B minus x for concentration B at time t. Okay. So we'll have to separate the variables, right? So we get dx A minus x times B minus x is K2 times dt. Okay, I have to go to a new page. So if we consider a special case where the initial concentrations are equal, so small a equals small b, right? Then this simplifies to dx over A minus x squared is K2 times dt. Okay, so this can be integrated quite easily using the initial condition as before. And so it leads to the integrated equation 1 over A minus x minus 1 over A equals K2 times t. Okay, so in this situation, you can see that this term will change linearly with time, right? So that's nice. So if we now go back to the more general case, so A is not B, then we go back to the original, right? So A minus x, B minus x. And this can be generally represented as d over A minus x plus E over B minus x. Okay, so now we have to figure out what these constants d and E are. And we find that d is B minus A to the minus 1 and E is A minus B to the minus 1. So if we fill that all back into the original equation, right, then we have 1 over B minus A dx A minus x minus dx B minus x equals K2 dt. Okay, so if we now integrate that and then apply again the same conditions like we did before, we get this ln B minus x over B A minus x equals K2 times t. Okay, so what is interesting that when B is not just bigger than A, but is hugely more than A. So if B is much bigger than A, so it's in B is in excess. Right, and this typically would it would be more than 20 or something. Okay, so since X can never be larger than A, then B minus A and B minus X, they will become almost indistinguishable from B itself, right? So then this whole thing reduces to ln A over A minus X, which is B times K2 times time. So if you work under large excess of B, the concentration of A will just simply reduce exponentially. And so we can say that the reaction is now pseudo first order. Even though it's a second order reaction, as we saw. So that is very frequently done in chemistry to determine the reaction order of the different reagents is by putting some of the is by taking one of the reactants in large excess and measuring the rate of the other reagent, right? So more generally, if we look at reaction equation, we can write in a general form dA dt A to the A, B to the B, C to the small c, right? The reaction order N is the sum of these coefficients, right? It's the sum of the coefficients. And so if we look at the initial concentrations, where they are equal to the stoichiometric coefficients, and we just say that all these coefficients for the moment are 1, then we arrive at this equation, or in the other notation we were using, dx dt is kn times A minus X to the power n, right? Which is the total reaction order. Okay, so if n is not 1, we can arrive at a general integrated equation. So we're not going to derive all of this, but I'm just going to give it, which is n minus 1 A minus X to the n minus 1 minus 1 over n minus 1 A n to the minus 1 is kn times t. Okay, so this is a very general relation that you can use for the different orders of reactions. Okay, so let's from this now try to derive a general expression for the half-life of a different order reaction, right? So we take this equation and we say the concentration of A at a certain time, right, time t, would be A over 2. So this is the same as in the other notation when you would say A is half times a initial. So we said that this is a minus x, and this is small a, right? So it's just the same way of writing, and that leads, after substitution, to t half equals 2n minus 1 minus 1 over kn n minus 1 a n minus 1. Okay, so this is the half-life for a general case, so where n is the reaction, the total reaction order. Okay, so also for the lifetime, we can express that in different ways, but what I want to just graphically represent now is how these two are related. Right, so if I look, for example, at a zero-ordered reaction, zeroth order, so we have the concentration of A versus time decreasing linearly. I told you before that when you reach this half concentration, you have T half. And for zeroth order, that is actually the same as tau. So that's nice and easy. However, if we go, for example, for first order, okay, we have this exponential decay. Oops, not exponential enough. Why? Okay, we'll have to leave it like that. So the half time is still where you reach half the concentration, right? And tau will be somewhere here. So that's for first order. And so for first order kinetics, I'll give you the equation. Tau is the integral of 0 to infinity of a e to the minus k1 t over a, which is 1 over k1. Okay, so that's still nice. What happens for second order, however, is that second order tau becomes infinite, because for second order the basically the integral doesn't converge over time, so it's not a very useful measure in all times, whereas basically the half-life is always defined also for second order.